Hello guys, and thanks for joining me again. We are going to be doing more math. Big surprise, I know, mind blown. Who knew? Math is what we're doing, but it is. So put your seatbelts on and drink your milk and let's get on with this and do us some math. Okay, I'm gonna click a button now. And there it is. So these two names that I can't pronounce and I'm not going to try to, were asked to reflect the pattern block figure shown on the left, which is this one, the left, over the horizontal line through the center of the square. They rearranged, words are hard. They rearranged the blocks to form the figure on the right. So we started out with this one, and they're asked to reflect over a line in the middle of a square to the figure on the right. And they want to know if they are correct. Spoiler alert, they weren't, because if they were correct, we probably wouldn't be looking at this problem. So let's kind of go through and see where they went wrong and why they went wrong. But first, let's start with reflection. Okay, for me, I think of Mulan and the song that I'm not going to sing for you because I can't sing. But so we have, oh, look, I put an animation on there. Let's watch that. So here's some reflection, right? Like I have the definition, but I know y'all are just going to look at the puppy GIF. So y'all look at the puppy GIF while I read the reflection. A reflection is a transformation in which a geometric figure is reflected across a line, creating a mirror image. I even have reflected the title up here a little bit. You can see that it's opposite. Think of how when you look in the mirror and you're wearing a shirt that has words on it, the words are backwards. That's your reflection. Like in your reflection, everything is flipped. It's the opposite of how it really is in the mirror. So that is something to keep in mind. But what they did is a rotation. A rotation has a point that stays fixed around everything else. I'm going to show you rotation on my video right here. Watch this real quick, this super cool magic trick, like this. Whee! So there's one rotation. And here is another rotation. See, same thing. Mine was more fun though. I had a blast. I would try it if I were you. I'm sorry, my cat is here. So there's a rotation, and as you can see, that's what they did. They rotated. They didn't reflect. So let's go ahead and draw a line of reflection. Remember, when reflect, it's going to look opposite. So we're going to, here's our shape again. We're going to reflect our triangle down, and we're going to reflect our trapezoid up. So now we're going to remove the original one, so we're going to end up with some funky little shape that's whatever, this thing. Okay, so now we're going to look at symmetry. First, we're going to look at reflectional symmetry. Again, we went over reflection. So this time we want to think of two things, like you have a piece of paper or a butterfly. Think of a butterfly. A butterfly is the perfect example. A butterfly got reflectional symmetry like right down its abdomen. So this side of the wings is the same as this side of the wings. So if we fold it in half, they're going to match the design and everything. It's symmetric. It's perfectly the same on each side. So we're going to see how many lines of reflectional symmetry each one of these shapes have. The first one has none. There's nowhere that we can fold this in half and have the same, because if we fold it in the middle this way, this little notch up here is going to be on top, and then this is going to be at the bottom, and it doesn't work that way. If we fold it this way, we're going to have that same problem because this notch is up here, and this notch is down here, and it just ain't going to work. Just trust me. Okay? So now we're going to look at this diamond shape. And this one actually has two lines of reflectional symmetry. So let's see where they are. Well, there's a one. What do you look at that? And notice something that kind of is a good indicator of if it's reflectional symmetry or not. We see right here that this is an equilateral triangle, and on the bottom is also an equilateral triangle. But not only that, but they're the same equilateral triangle. They look the exact same. That's how we know we have found a good line of reflectional symmetry, because each side of that line looks the exact same. So is there another one? Bum, bum, bum. Well, I already said there was, so, but let's see where it is. Oh my, we found it. And now look again. We see that these are 4 right triangles that we have now created, and they all look the same. That's how we know we have successfully found our reflectional symmetry. So there is 2 lines. This one, this one kind of looks a little bit similar to the first one, Kat. It's just a little more squiggly and slanted. Not squiggly, just slanted. Let's pretend I did not say squiggly. I didn't say squiggly, okay? It's just more slanted. So, does this one have any lines of reflectional symmetry? No, it don't. So now we're going to look at the equilateral triangle. It has 1 line, and there it is right down the middle. We can see we've got 2 right triangles that are split up into that looks the exact same on both sides, so we have our line of reflectional symmetry. What about a semicircle? 1 line again, because if we try to fold it in half, hot dog wise, didn't think I remembered hot dog hamburger, but I just did. If we try to fold it in hot dog wise, which is long way horizontal, it wouldn't line up because the bottom is curved and the top is straight, so we can't do that. So what about the rectangle? Rectangles are fantastic. It too has 2 lines of reflectional symmetry. 1 and a 2. And our boxes are the same. 1, 2, 3, 4 boxes. Same size. We've just created more rectangles. Bam. There you go. And then our triangle right here, our isosceles triangle, has 1 line. And this one got, oh my goodness, it's got 4 lines. And looky there, our triangles are all the same. Beautiful. It's just so beautiful. So now we're going to look at rotational symmetry. I only chose a few of the shapes, but I chose shapes that kind of have each a different type. So first, let's look at our first polygon. I don't know what you call it. So rotation, again, keep in mind, is we're going to spin it. So I'm going to do that one more time. We're going to spin our shape and see if there's any symmetry, meaning when we spin it, does it look the same as it does right here? Spin it. It's just fun. Let's just do one more time just because it's fun. Whee! Okay, now let's go back to math. So here's it spun this way. Is it the same? No, it's not. Let's spin it 90 degrees again. Oh, that looks the same. So we do have rotational symmetry right there. And oh, funny, that one looks the same as that. That's kind of weird, Kat. So this next shape, we're going to go to this isosceles triangle that is on its side, and we're going to turn it. That doesn't look anything like it. It's not the same, Kat. It's just not the same. Okay, well, let's keep going and see if this next one's going to be the same. It's not the same. I'm sorry, it's not. And this one? No, not the same. So this doesn't have any rotational symmetry. And this one? The equilateral triangle? Ooh, we're going to turn it. We're going to turn it. We're going to turn it. Oh, girlfriend. It got it. Okay, so now we're going to look at vertex tiling. I forgot the term. I'm so sorry. So Myra is giving the task to make a tile out of some shapes. And this is what she comes up with. So think of tiling as, you know, bathroom tile, or, you know, something you would see in like an old dormitory that's just really ugly and doesn't make sense. Like for me, the first thing that comes to mind is those white squares that have like the little green squares that look like diamonds because they're turned in between them. Like that's what I think when I think of tile. Even though it's ugly, it's all coherent and it fits together and it's repetitive and it's constant. So that's what we're going to think of for tiling. So for tiling, we want no overlapping and no gaps, and we want to repeat the same thing over and over and over and over again. And they all have to meet at this vertex, right? The same way. So Did she do it? I mean, it looks okay right now, but what if we continue it? So let's go ahead and add another pentagon. That doesn't really work. There's a gap, and it like there's nothing that can fit right here. Well, maybe I just put the shape on them wrong. So let's go ahead and go to the other side of the pentagon and add another heptagon. Words are hard. Look, it doesn't fit right here. There's like a little space, and then there's a teeny tiny little gap right there. No bueno. Not good tiling, Myra. I'm sorry, but let's do our own tiling. So let's again start with this hexagon, and I'm going to go ahead and keep her same idea where I'm going to alternate shapes. So I'm going to have 4 of one shape on the hexagon and 4 of another shape. I chose to do more hexagons. And the reason I chose to do hexagons is because these hexagons are beautiful. All their sides are the exact same. Their angles are all the exact same. There's nothing funky or wonky about them. So they all are going to fit together perfectly no matter which way we turn them. They've got great rotational symmetry. So they're great for this. So now I'm going to go ahead and add in my other shape. I have chosen square. Look at the square. Look at it. It fits great. Ooh, but Kat, what if we added more hexagons? Now, would it still be a good tiling? You bet it would. Let's go ahead and test it. And there we go. And then we would continue our shape. We'd add more squares right here, more squares right here, more hexagons, so on and so forth. So the tiling works. It's very coherent. It fits together. We've got our shapes done. They're all the same size, the same angle. Their rotational symmetry is there. We can turn it whatever way we want, and it's going to be the same. Great. We have tiled. We can now all be architects. Let's go sign up for architect school right now together. Just kidding. I tried to build a doghouse in 3rd grade. Okay, so this we are going to look at. We're going to demonstrate some things over here to learn with some words, because words are fun. We love words. Like, who needs pictures, right? We got words. Kat, this is in English. Let's just use pictures and numbers, not words. That's disgusting. Okay, fine. You've convinced me. So this, does it look like something that we have played with when we were children, or maybe even now? You're lucky if you can play with them now, but to me, it looks like a kite. And the shape is actually called a kite. So kites have one line of reflectional symmetry, and it's right down the middle. So as I've stated before, when we find this reflectional symmetry right down the middle, we're going to have 2 sides that are the same, or 2 shapes that are the same on the side, whatever the shape may be. In this one, they just so happen to be scalene triangles, which scalene triangles mean that none of the sides are the same, but it's still a triangle. But they're congruent scalene triangles, and we know that for a fact because one, like I said, has got reflectional symmetry. And if we were ever in doubt, we can go ahead and see right here, we've got our little tick marks that mean these 2 lines are equal to each other, and these 2 lines are equal to each other. And then we know this base is the same on both sides because they share a base. So of course it has to be the same. So this is how we know that these triangles are going to be congruent. What about angle QPT to SPT? So QPT to SPT. Girlfriend, again, we just cut it in half. It's got to be the same on both sides. That's what happens when you cut something in half. The only exception to that is when you're sharing a sandwich with your siblings and you cut it and you give yourself the bigger half on purpose. But that's not what we're doing. This is math and we're doing it perfectly great. So now we're going to demonstrate why QPV, and SBP are congruent. So again, let's go ahead and pretend that right here we've just got an isosceles triangle, right? So let's just go ahead and eliminate this down here, this other triangle. We're just going to look at this one up here. Excuse me. So on this one we have a Dun, dun, dun. Isosceles triangle. I already said it, but I'm saying it again because that's who I am as a person. Anyway, so we're going to have it right here, and it has one line of reflectional symmetry. And what have we been saying about one line of reflectional symmetry this whole time? When we cut it in half, it's going to be the same on this side and the same on this side. So we have cut this in half. It is symmetric. That line tells us that we have cut it in half. It is symmetric. So that means that this side and this side are the same. Easy. So finally, we're going to look at why QVP is a right angle. What are perpendicular lines? What are perpendicular lines? Hello, class. Can I hear you? I don't hear anybody. Oh, I don't have class. Sorry, I forgot. Perpendicular lines are when two lines intersect at a 90-degree angle. 90 degrees. The right angle. In case you forgot. So this right here are perpendicular lines, which means they're meeting at a right angle. Bam. Mind blown. Knowledge. Just like that. Let's go. Oh man, I have goofed up. We have a little bit of spoilers on this slide, but it's okay. You don't know what they mean, so whatever. So we're going to start out with a circle. A whole circle. And we're going to inscribe, ooh, fancy word, just means we're going to put inside, that's bad wording. We're going to put a triangle inside this circle, just like this. There she is. And now we're going to section off this triangle into 3 pieces, each corner. Beautiful. Just look at it, draw. So we're going to divide the amount of sides on the triangle, the corners of the triangle, by 360 because 360 is the circle. So we're going to get 120. We're going to do it again. We're going to inscribe a pentagon this time, which is 5. We're not inscribing the building in Washington, D.C. inside a circle. We're doing an actual pentagon. Okay, in case you were confused, I can clear it up for you. So here we go. We've got our pentagon with 5 sides, and we're going to break it up. And again, we're going to divide, but this time we're going to divide by 5 because pentagons have 5 sides. 1, 2, 3, 4, 5, and we get 72. So now we're going to put these beautiful shapes together within one circle. And we're going to go ahead and cut it up even more and add some more lines because why the heck not would we do that? Hello. So when we do that, we're going to have this little funky shape and this little funky shape, and we're going to need to find the measurement of it. So we are going to subtract 120 from 72. We get 48. Are we done? No, because we still have to, cut it in half again, and that way we will get 24. Okay, so Guinea, my friend Guinea, is deciding that she wants to measure a mountain from half a mile, quarter mile away. She's kind of strange, but you know, we just kind of like Guinea be Guinea. But so she's holding up a ruler 2 feet in front of her face, and she's got tick marks on the ruler. And the tick marks are 1.5 inches apart. And she's holding the ruler 2 feet from her face, as we stated. Maybe not, I forgot, but I'm going to say it again. So we want to use, we're going to find out the height of the cliff using ratios, which I love ratios, and I'm going to show you why. Ratios, they're beautiful. So beautiful. So let's go ahead. So we see a triangle right here and a triangle right here. These triangles are the same. They're congruent. They're not similar, because similar would mean they're the same length. They're congruent, which means they have the same angle measurement, which is very important to keep in mind. So our ratio is the distance between the ruler markings and the distance between Guinea's eyes and the ruler equals height of cliff over a quarter of a mile. So we've got most of this information. So we've got 1.5 inches over 2 feet equals x. X is what we're looking for, and that's the height of the cliff, over 5,280 divided by 4, because there's 5,280 feet in a mile. And we're dividing by 4 because it's a quarter, and a quarter is 1/4. And we're going to go ahead and convert everything into feet so we can set up our ratio. So here we have it set up. So now I'm going to do something that I love. It's my favorite thing in math. I love doing this, and that is cross multiplication. It's beautiful. You can use cross multiplications for so many things. And a ratio is one of them. So we're going to use it. So for this, we're going to draw our little x here, which means we're going to multiply these. So x is a missing number. So we're going to multiply 1,320 by 0.125 and divide that by 2. And when we do that, we get 82.5 feet. So that is all I have for you guys. Thanks for joining me on my crazy math adventure. If you have any questions, feel free to ask, although I probably won't hear you because this is a recording. But, again, you can feel free to ask. Doesn't mean that I will, oh, that's my face. Doesn't mean that I will, be very good at responding. So, thanks for joining, guys, and have a great day.